Hello everyone, thank you for joining us today. This evening, Professor Gheondea, one of our department's professors, will deliver us a speech on spectral theorems. He has studied this topic for several years, and now he will share his experiences and thoughts on this topic with us. Again, thank you, Hocam.
Thank you, everyone. So, we mathematicians are not that formal. Thank you. Anyhow, so the story of this talk is the following. The Bilkent Mathematics Society, which is actually made by students from our university, invited me by their representatives, Aurelian and Mohammed, to deliver a talk about analysis. But analysis is a huge topic, and I don't feel competent in talking about analysis like that. So we negotiated, and I suggested two topics. One of them is spectral theorems, and hence this is it. But I will try my best to put these mathematical theorems into very large historical perspective. So my goal is somehow to show that the roots of these theorems are actually back 2000 years ago in Greek geometry. And a lot of the most famous mathematicians that contributed to mathematics in an essential way actually marked the way on getting these theorems. I will also try to explain how these theorems are related with other disciplines. So our journey will start about 2000 years ago, and we'll end up in these days connecting classical Greek geometry with quantum mechanics. Why we are so interested about these theorems. So the plan is this. One more thing. The organizers told me that they planned the talk for about 1 hour, and then there will be discussions, questions. But I invite the audience, if there is anything that you don't understand, or you want me to clarify, you have questions, please don't wait until the end. Ask, and I can try to answer. So I would like more this talk to be like a dialogue than a monologue. I hate monologue. So the plan is that the talk is actually split into two parts. A short history of the spectral theorem. I will start with conic sections. Then I will visit René Descartes, the principal axis theorem in analytical geometry, and then pushing this into infinite systems of linear equations. And finally, I will reach, hopefully, I will reach this mathematics part, the three forms of the spectral theorems, which are the spectral measure form, the multiplication operator form, and the spectral multiplicity form. So the story starts with conic sections. What is a conic section? It's a curve which is obtained as the intersection of a right cone. What do I mean by a right cone? I have a circle, and I have a cone which projects exactly in the center of the circle. Yeah. So this is what I call a right cone. And then we cut it with a plane, and we obtain some sections. We can obtain a circle, we can obtain an ellipse, we can obtain a parabola, we can obtain a hyperbola. The hyperbola is a little bit more sophisticated because you have to extend the cone with the upper part, and hence the hyperbola actually will have two branches, one here and the other in the upper cone. Okay, now we actually start our excursion, in business, right? Very close of here, because there was this guy, Aurelian of Perga. So Perga is a Hellenized name of Pamphylia, which is in Anatolia. Currently is a village, Axum, in Antalya region. So he has read a whole book about these conic sections from the geometric point of view. So alternatively, one can define the conic section in terms of plane geometry, not like these sections. So it is a locus of all points P whose distance to a fixed point F, called focus, is constant multiple. That constant P is called the eccentricity of the distance from P to a fixed straight line. Here is a picture. So for the case of an ellipse, this ratio should be constant, and the point is moving on the ellipse. For the case of the parabola, again, this ratio is constant, but now E is 1. In the case of the ellipse, it's strictly less than 1. In the case of hyperbola, the eccentricity is strictly larger than 1. So for each eccentricity, we obtain a different shape. In the case of the hyperbola, as I said, we have two branches, this one and the other one. Okay, now we are going to make a jump. This is my favorite part. René Descartes. The picture is from Encyclopedia Britannica. This guy, René Descartes, is considered to be the founder of the modern philosophy, and in the same time, the founder of the modern mathematics. This is extraordinary. So, look, he lived back in the 17th century. He had a very complicated life. He was a Catholic, but he found shelter in the Protestant part because it was the time of the riots of this 30 years, they call it the war, the 30 Years' War. So anyhow, from the philosophy point of view, he abandoned completely the scholastic Aristotelian. He formulated the first modern version of mind-body dualism, and he promoted the development of a new science grounded on observation and experiment. And he dismissed completely knowledge derived from authority, the sciences, and reason. But reason, be careful, this means just speculation. You know something and then you're making speculation. He said, forget about this. And in philosophy, he's best known for his, I think, therefore I am, in Latin, cogito ergo sum. Originally is je pense, donc je suis. But we are going to look at René Descartes, Cartesius, with his Latinized name, as a father of modern mathematics. Why is that? I am quoting Sir Isaac Newton. He said, if I have seen farther than others, it is by standing upon the shoulders of giants. One of the most important giants on whose shoulders Newton stood is René Descartes. Why? Because he created analytical geometry, which is the bridge between geometry and algebra. So now I try to write something. Let me see how things are going. So, from the point of view of the main domains of mathematics, geometry was the first. Geometry means somehow measuring the earth. But in mathematics, you know, names most of the time have nothing to do with a meaning. And then it was algebra. Algebra came later. But for a very long time, they have been separated, completely separated. Geometry was done in one way, algebra was done in another way. Okay, the baby sister is analysis. Analysis is the youngest among these siblings. But what Descartes did, he created a dictionary between geometry and algebra. And this is what we now know Cartesian geometry. Okay, I will come back to this later. On the way, we have to cite also Johannes Kepler, which formulated and explained the motions of the planets in the solar system that follow exactly conic sections. Most of them have elliptic trajectories. There are some having parabolic trajectories. The comets, there are comets that are coming and visiting our solar system, and then they go and then they never come back. They have parabolic trajectories. But coming back to Sir Isaac Newton, he made the first mathematical model of classical mechanics that is now called the Newtonian mechanics. And this is based on differential and integral calculus. So this is a reason why Newton wanted to have what we call now calculus, because he wanted to create the Newtonian mechanics. His most important book, Mathematical Principles of Natural Philosophy. So the subject is natural philosophy, not the principle of mathematics. He was especially interested in making mathematical models for physics and especially mechanics. Okay, now what is the first mathematical statement of a theorem that we can call the spectral theorem? In modern terminology, it has the following statement. Any symmetric quadratic form, and here I'm writing the formula, sum ij from 1 to n, alpha ij, xi, xj. So xi and xj are the variables. Can be written by means of an orthogonal transformation from Rn into Rn into the normal form, sum I1 to n, lambda I xi squared. Now, in order to understand this statement, one more comment. My students told me you have to be aware that the audience will be made by students in mathematics, students in philosophy, students in engineering. And I said, wow, this is very challenging for me. How can I make happy everybody? The problem is trying to make happy everybody is that most of the times you can make everybody unhappy. So if there is too much mathematics for some of the audience, please let me know. If there is not enough mathematics for some of the audience, please let me know again. So I'm trying to give something to everybody, but in the end, I am guilty as charged. So let us try to explain the statement. We say symmetric quadratic form. Why symmetric? Symmetric means the following, that alpha ij equals alpha ji. So if I switch the indices, I'm getting the same number. They are the coefficients. Why is quadratic? Because all these terms are actually of order 2. They are products of 2 variables. That's why we call it quadratic, of order 2. Okay, what is an orthogonal transformation? An orthogonal transformation is a transformation that does not change the distances. We call it isometry in general. It's a linear transformation for students that know some linear algebra, the linear transformation from Rn into Rn, usually modeled by a matrix. And this matrix have columns with a certain property. We're going to come back to this. And this is the normal form. Look, if you compare this with this one, it looks much simpler. It contains only the square. Yeah? and some coefficients here. So this is a principal axis here. It is not clear from here why we call it principal axis. We're going to see it immediately. And it's not clear why we're so interested in this kind of things. Okay, some history.
Can you explain, for example, what Descartes and then equals to?
Sorry?
Can you expand upon what exactly Descartes did?
Yeah. Thank you for the question. You see, the job of a good speaker is always to make the answers in the next slide. For any question I get, and say, okay, your answer is on the next slide. Thank you. You made my day. So it will be in the next slide. So René Descartes in large geometry, he did it for n equals 2. N equals 2 means that we are working in the plane. We have a quadratic form in two variables. But a lot of mathematicians contributed to it. So Pierre de Fermat, Leonard Euler introduced the term principal axis because he related with the mechanics of rotation values. Then Joseph Louis Lagrange, or you know, Lagrange was born Lagrangian. There is a building in Milano, which is stating that here Giuseppe Luigi Lagrangia was born. But his family migrated to France, and now we are using the French name. Jacobi. Jacobi is a guy, advanced calculus, that we are struggling now. The Jacobi matrices of the total pressure derivative. Yeah. Sylvester and Cayley, the great English mathematician that somehow founded linear algebra. And finally, the German mathematician Georg Frobenius, he put this into the analytical geometry terms. Sylvester and Cayley put it into language of matrices and eigenvectors. And this is what we are going to do for the case n equals 2. So, Mohammed, your passions is rewarded. Let's take n equals 2. The general form of a conic is this one. So it has second order terms, x squared, y squared, x squared. It also has first order. If you are making a translation, you can put it into this form, which is now looking exactly like a quadratic form. We have only terms in which you have x squared, xy, and y squared. And mu is a constant. And this is what we are going to do. So now we are using the matrix, the linear algebra approach. We, okay, I write it here 2 times bxy. Why? Because actually we have bxy and byx, yeah? But because multiplication is commutative, we actually write them 2 times bxy. And by keeping this in mind, we have this 2 by 2 matrix, A, B, B, C, B, C, so B applies twice here. But this is wonderful. Why? Because it makes the matrix symmetric. So if you make the transformation, you are not changing your matrix. And this is, if you remember in the statement of the principal axis theorem, the symmetric quadratic form, yeah, it's coming from here. And then we are using the usual scalar product for pairs, x, y, z, and y. And hence, this quadratic form can be written in this way. So it's a matrix A multiplying with the column vector xy, and then in a product with the column vectors xy. So we have exactly the quadratic form into variables. And now we go into linear algebra. We have a square 2 by 2 matrix. We are looking for the determinant of lambda I minus A. This is what is called characteristic polynomial. So if we calculate this matrix and calculate the determinant of a 2 by 2 matrix, that means the product of the elements on the diagonal minus the product of the elements on the off diagonal, we are getting, after a little bit of algebra, this second order polynomial, lambda squared minus a plus b lambda plus ac minus b squared. But as you will know from elementary, the trouble with second order polynomials is that they may have real roots, or they may have no real roots, depending on the discriminant, yeah? Let us calculate the discriminant for this. It is a plus c squared minus 4 times ac minus b squared. If you do some algebra here, you can write it as a minus b squared plus b squared, which is wonderful because we know that this is always non-negative. I don't want it to be 0. It can be 0 only if b is 0 and a equals c. This corresponds somehow to the cycle. Yeah? And we're going to see that this is somehow special case. But at least one of these conditions, I don't want it. So either A is not C or B is not 0. And then from here, we can calculate the roots of the characteristic polynomial and get lambda 100. We know how to do this. Since this is not 0, yeah, lambda 1 and lambda 2 are different. The two eigenvalues are different. And then we got the connection with our principal axis theorem for n equals to what actually René Descartes did, but of course he did it in a completely different way. So if lambda 1, lambda 2 is positive, that means the two roots lambda 1 and lambda 2 are either both positive or both negative. We have the ellipse case. If lambda 1, lambda 2 equals 0, which means that at least one of the eigenvalue is 0, then we have the parabola. Parabola is a kind of very special case, yeah? If you look for that, if you remember that picture. If lambda 1, lambda 2 is smaller than 0, meaning that one root is positive, the other is negative, we are in the hyperbola case. Okay, but we are not happy only with this. We go further. Lambda 1 and lambda 2 have the interpretation of eigenvalues. Okay, now I'm writing this magic word, eigenvalues. Which is a strange word. It's half German, half English. So eigen is a German prefix, means proper. Okay, value, it's an English word. Why we call it eigenvalues? Because a lot of mathematics was done in Germany, and then some of the mathematicians migrated to United States, and they combined their root, their German root, with a new word, English speaking. So we have this very strange word, eigenvalue. And this will be somehow one of the magic words in this talk. Okay, how do we connect this with principal axis? Because A is symmetric, it can be shown that the two corresponding eigenvectors, so the eigenvectors are calculated according to this way. AX1 is lambda 1 x1, and AX2 is lambda 2 x2. So geometrically, what does it mean this? That we have two directions in which the action of the matrix is not changing, yeah? So the vector x1 is mapped by A to a vector which is collinear with it, yeah? And similarly for the vector x2. And because of this symmetry condition, it can be proven that the two vectors x1 and x2 are actually perpendicular one to each other. Keep in mind that n equals 2, so we are working in the time, yeah? And these are the principal axes. But actually, what we get by these eigenvectors is much more. So we do the following. We now make the matrix with x1 as one column, x2 another column. we encode this the matrix U. U will be the orthogonal transformation, that which is making the rotation. And we calculate A times U. Now, this is the matrix with these columns, AX1, AX2. But AX1 is lambda 1, AX2 is lambda 2, AX2. And this can be shown that it is actually the matrix U times this matrix, we call it diagonal. Lambda 1 and lambda 2 are the diagonal and 0, 0 are the orthogonal. And we can write it because U is an orthogonal matrix. That means that the transpose of U is the inverse of U. We can write that U transpose AU is the diagonal matrix lambda 1, lambda 2. So in this way, what we did is a thing that is called diagonalization. And then if you go into the quadratic form representation, this new matrix which you obtain by these two rotations provides exactly the normal form of the quadratic form. Okay, apologize for students that think that mathematics is too much, but that's only the beginning. You have to prepare for more. So here in this toy example, we are seeing a lot of ideas. So I kindly ask you to keep in mind this model because we're gonna fly very high. We're gonna fly higher than the nimbus clouds, probably close to the moon or even much higher. So you have to take your breath. You have to buckle your seat belts. And not to lose your breath.
Can I say?
Okay. Anytime.
This is a linear transformation. So can we say that it transforms a circle into an ellipse or a paraboloid?
No, it doesn't change. It doesn't change the conic section. The conic section is the same, only that we are changing our system of coordinates. See? By doing this transformation with U, we are starting from here, from the canonical system E1, E2, into another one.
I thought a circle on the first plane is not going to.
No. The transformation is not changing in any way our quadratic form. The conic section will remain the same. The only thing that we change is a system of coordinates. Yeah, we can make translations and we can make rotations. So the matrix U is making the rotation. Why is that? Because your ellipse can appear like that. See? So actually, what we are doing, we are founding exactly the axis which somehow correspond to the normal, or in this way. We are not changing the curve. We are changing our system of coordinates. Okay. Now, you know, mathematicians are never happy. They are the kind of profession in which no matter what you are doing, you find another problem. Please.
Or our change of coordinates can change the whether it's a right hand or left hand.
We also can have symmetry. Yes. So orthogonal symmetry is also so there are actually two types of orthogonal transformation. One is rotation, and the other is symmetry. Yeah. You're right. Okay, but now, as I said, mathematicians are never happy. They are always unhappy. Why they are always unhappy? Because at the end of any result, they got other questions. So a lot of analytic geometry has done, but there have been other questions. What about, you see, well, what we did so far, it's about a finite number of equations, yeah? We have matrices of finite order. But the question is, what is happening if we have infinite matrices? With infinite number of rows and infinite number of columns. here I want to justify why these objects are so important. Because, okay, mathematicians have a bad reputation. People think that we are living with our mind in the clouds. And to a certain extent, this is true, believe me. Okay, now Joseph Fourier attempted to show that every function can be expressed as an infinite linear combination of trigonometric terms. Le principe de réduit means to solve the first n times n system. So we're making actually a truncation of it, and then make it n larger and larger, yeah? So letting n approach infinity. Now, Theodor Kretevich from Saxonia, a physicist, extended Cramer's rule for infinite determinants. Hill, an astronomer, applied the theory of infinite determinants to the stability of the motion. Or Appel applied le principe de réduit to power series with functions of elliptic functions. Okay, what is elliptic function? Forget about it. It's a complicated. My colleague, Professor Kaptanoglu, will teach you what elliptic functions is, if you are curious about it. But it's a long story. Henri Poincaré provided rigorous definitions of infinite determinants and clarified the words of Hill and Appel. And then Poincaré developed an extensive theory of infinite determinants. So matrices with infinite number of rows and columns, if you can imagine. But things never stop here. So Abel, a genius Norwegian mathematician who died unfortunately very early, used an integral equation to generalize the tautochrome curve problem. Does anybody know what the tautochrome problem is? It's a wonderful classical problem. Let me state it.
And if you are such that wherever you drop the ball from it, it's and at the same time.
Okay, now let me translate what Albert said. So 90% of Albert's answers are correct, but they have to be translated into plain English. So, Hawking is a curve with the following property. You assume that you have in the gravitational field, and there is no friction. And no matter where you put here a material and you let the gravitation work, the time for traveling this material point from here to the end point is the same. If you start from here, if you start from here or from here, the time is the same. Yeah? The name of this curve is called a cycloid. And it's a very important problem. That's why it is called isochrone. Iso means same time. But anyhow, he reformulated into this integral form. And this was the beginning of an extraordinary development of mathematics. Why? Because Joseph Levy introduced the method of iteration for some integral equations. And then Carl Neumann extended this for boundary value problems for harmonic functions. Now, once again, my colleague, Professor Kaptanov, is a specialist in harmonic functions. If you are curious about harmonic functions, his, I think the last 10 years research is considering multidimensional spaces of harmonic functions. Then Vito Volterra, an Italian mathematician, introduced the famous Volterra operator. Volterra operator is an integral operator, but you have to be very careful here because this is misleading. Here it's a kernel, but the kernel is something like that. Yeah? It's on this kind of triangle. See, because we are integrating this from 0 to x. Okay. Now, we don't know what capital L2 is, but I will give you some intuition immediately. This Volterra operator is an extraordinary operator. By operator, I always mean a linear transformation. Why? Because it's a compact operator. What is this sigma P of B is empty means that it has no eigenvalues. So you see, in infinite dimension, if you can imagine a matrix in infinite dimension, there can be matrices having no eigenvalues at all. In finite dimension, this is not true. According to the fundamental theorem of algebra, any square matrix has exactly n eigenvalues counted multiplicities. And this is what we call the point space. I will give precise definitions in a moment. On the other hand, this V, the operator lambda I minus B, is invertible everywhere where lambda is not zero. This means that the spectrum of V has only one value, zero, but this zero is not an eigenvalue. It's something else. So watch out, check your seat belt, because now we are going to fly very high.
Or having donuts.
Okay. Now what happened? Spectral, a Swedish mathematician, applied the theory of infinite determinants for integral equations. And now we already know here. So this integral has a kernel, k of xy. Okay, the problems that we studied are of this type. And by using the Daniel Bernoulli ideas to represent vibrating string as the limit of n oscillating particles, he viewed this integral equation as the limited case of the linear system. So here is a discrete version of this discretization, what we most of the time do. And now we go into differential equations. Sturm and Duvier. Okay, Sturm is a German name, but the guy is actually French. Jacques Charles François and Joseph Duvier. They consider this differential equation. Sturm-Liouville equation is extraordinarily important. Why is that? My colleague, Dr. Jihan Okai, is doing quantum physics, and he will tell you that this is a very interesting equation, which is related to one of the mathematical models in quantum physics, the Schrödinger model. We're going to see that. So when this function p equals 1, we are getting exactly the Schrödinger equation, minus b squared y to bx squared plus q of x1 equals something. This q of x is called the potential. The first part is nothing else than the Laplace operator that students from advanced calculus, we just saw it in multi-dimension. So this equation may look very innocent, but it's not. For different type of potentials, magnetic, electromagnetic, this kind of things, solving it means that you can solve a very big problem. And most of the physicists working in quantum physics, they are doing exactly this, if they apply the Schrödinger model, because we are going to see that there are more models. Okay, we have here the weight function. W is a density function. A Sturm-Liouville problem is called regular if we have some conditions on the coefficient functions, but usually they come accompanied by some boundary conditions. These boundary conditions are extremely important because if you remember what we did for matrices, we did something for the case when the matrix is symmetric. How can we say that a differential equation is symmetric? Well, there is a problem. The boundary conditions are extremely important about this. They give us the symmetry or not. Okay, now we come to the core of our talk. The value of lambda is not actually specified, and the goal is to find the values of lambda for which there exists a non-trivial solution. But what does it mean, non-trivial solution? It means that somehow you can invert the problem. Yeah? Solving an equation means that you have an inversion. Okay. And we want the boundary condition to be satisfied. Okay, now we got the big guy. The big guy is David Hilbert, one of the greatest minds of mathematics in the first part of the 20th century. So according to Hermann Weyl, who was his PhD student, when David Hilbert heard about Fredholm's investigation, he literally caught fire at once. So for the next 10 years, he dedicated his life to understand these problems in infinite dimension. So he has a series of 6 articles from 1904 to 1910 in the Bilkent Mathematics, in which he investigated these integral equations. Now we have this. Okay. There is something that instructors in the course of differential equations should tell students. You know, we usually work with differential equations, but any differential equations can be put into the form of an integral equation. So the theory of integral equations is more general than the theory of differential equations.
And they are usual base with
Yeah, you can have a lot of things.
Kernel of a differential operator.
No. Kernel has a different meaning here. Kernel, we use this with this concept with the following definition. It's a function of 2 variables. This is a kernel function, yeah? Not kernel like the null space of a matrix. Yeah. Sorry for this. So Hilbert was a guy to define the spectrum, but there is a very nice story about this spectrum. He defined it for quadratic form, distinguish point spectrum eigenvalues from continuous spectrum. Hilbert defined the concept of complete continuity, compact linear transformation. And then here, there's a lot of, it's wonderful mathematics, analyzing the kind of the elements in the spectrum. This is what we call spectral theory. And Hilbert actually formulated the first spectral theorem, not only for completely continuous forms, but for bounded forms as well. Now, some more history. Schmidt actually was the one that coined the space algebra. You know, Hilbert never worked with a space that now we call Hilbert space. This is fun. So he did a lot of things and used grammar orthogonalization, which is now called Gram-Schmidt, in order to define many interesting mathematics. So Hellinger was on the way. Hermann Weyl, one of the giants of mathematics as well, a PhD student of Hilbert, he made extensive study on bounded forms. Frigyes Ries, Hungarian mathematician, he contributed essentially to students that will reach somehow the function analysis course. They will learn a lot about this. There are a lot of these theorems.
What does form?
Form means a map which is defined on a space and has scalar values. Linear functional, for instance. We call them form in order to separate from linear transformations. When we have scalar values, we call them forms. Quadratic form is a form because it produces numbers, yeah? It gets vectors and produces numbers, so scalars. Normal form is a spatial representation of a form. Other questions? Please, if you don't understand something, ask. Okay, now we get to quantum mechanics. At the beginning of the 20th century, there have been a lot of experimental atomic physics, and the researchers got into a lot of trouble because of the following phenomenon. they wanted to do experiments. And the experiments were quite expensive, and they wanted to do experiment A. And then they wanted to do experiment B. But sometimes they are doing it in the other order. And to their surprise, they got different results, different measurements. And they say, come on, what is happening? If I go from here to there and from there to here, I'm doing a similar thing. Yeah? So commutativity is somehow in the human mind. But at this atomic level, commutativity is different. It's something else. It's a different word, and they couldn't understand it. So Heisenberg, who was a very good student, he then remembered, oh, there was a crazy mathematician. He was teaching me about matrices. And you know, these matrices have this strange property. If we multiply two matrices in this order, they usually are different. And he said, okay, this is a good idea. And that was a starting point for Heisenberg to find his famous first mathematical model for quantum mechanics, which is based on matrices. By the help of this Christian Masborn and Pascual Jordan, they represented physical quantities by appropriate finite or infinite matrices. And the set of possible measurements have been integrated by spectral values, eigenvalues. So actually what in experimental physics they get, the numbers they were getting, they were actually eigenvalues. Okay, now we got another giant, Schrödinger. Schrödinger introduced the concept of wave function. And he stated his famous time-independent equation. This guy from here, some of the students may probably don't even know how to read it, is nabla square. It's actually the Laplace operator. So in one dimension is t squared f to dx squared, right? In multi-dimension, it's another story. You have to use a gradient, you have to use a divergence. We did this in our advanced calculus course. So he gave a derivation of the wave equation for time-independent system and showed that it gave the correct energy eigenvalues. Most of the time, the linear transformation that is modeling a physics system is called Hamiltonian, from Hamilton, an English mathematician. But then came another guy, Dirac, and he noticed an analogy between Poisson brackets. If you don't know what Poisson brackets is, forget about it, and classical mechanics. And the recently proposed quantization use of Heisenberg, lattice formation. And he did it in a completely different way. So actually, he's famous for somehow splitting this guy into two parts. He separated it like that. And he called, you know, he used, here we have a bracket, and then he split it into two words. One is bra, the other is cat. No other implication. Just a coincidence of name. One is bra, the other is cat. So he has this mathematical modeling of quantum mechanics in terms of these bra and cats. And then we're going to reach a very difficult problem, because this is something which was a problem for a very long time. Now, John von Neumann, another genius guy, he set the foundation, the solid foundation of quantum mechanics. He introduced the concept of linear operator in an abstract Hilbert space, expressed the transformation theory of quantum mechanics in terms of operators in Hilbert spaces. We are going to see that more clearly in a moment, and recognize the need to expand the bounded operators to unbounded operators. And this is a very big problem. How do you pass from bounded means continuous? So we are going to work with transformations which are not continuous. Okay. And then his contribution to mathematics is extraordinary. There is a whole domain called from Neumann algebras that together with his collaborator Francis Marais, he established in a series of papers. But we're not going in that direction. Okay, now let's fly a little bit louder. Most of the students have heard about Riemann integral, yeah, in calculus. Associated to the Riemann integral, there is a Gheondea measure. Gheondea is coming from this guy. He's actually a man. Marie, Camille, they are names for girls, but probably his parents were very unhappy not having a girl, a daughter. So here's Marie and Camille Gheondea. But Gheondea did wonderful things. He showed that associated to the Riemann integral, there is a measure. Measure is what? Is a function which is giving you some numbers. For instance, the length of an interval is a measure, or the area of a surface is a measure, or the volume of a body. Yeah, these are measures.
Orthodox rights.
Yeah, but there is a lot of trouble with the Riemann integral. Okay, students from advanced calculus know that Riemann integral is very limited in terms of exchanging the order of it with other operations. We need uniform convergence, we use all these kind of things. And it was this guy, Aurelian, in the mathematical genealogy, he is one of my ancestors, grandfather. He invented the Lebesgue integral and the Lebesgue measure. Now, students that are taking Math 314 with Professor Kapanov probably all know what it is. Lebesgue measure and Lebesgue integral. Then Constantin Theodori pushed things into abstract measure and abstract integration. Then we have this Lebesgue spaces LP, but we're going to be concerned mostly with Lebesgue Hilbert space LP. So this is defined in the following way. If mu is a measure, there are all the functions of a complex value is a property that the square of the absolute values is integral. And then you have this scalar product of two functions. You know, in mathematics, many times we consider functions as vectors. And this is a little bit demanding for students. Sometimes they don't understand it, but that's okay. Now, what about Hilbert spaces? The simplest one is small L2. Small L2 consists in all complex frequencies with the property that this series of the squares of the absolute value is convergent. And then we can define the scalar product. You see, if here you just put it on some n, you are getting the scalar product from the Euclidean space. But here we are working with series, so we are already in the infinite dimensional space. In general, we consider this capital L2. You have a measure on a measure space, a sigma algebra. I'm not coming into elements. Anyhow, the inner product is given by the integral of f times this is a complex conjugate of the function g. Now, in Hilbert spaces, one of the most important problems is that of orthonormal basis. Orthonormal means the following, that any two different vectors, En and En, are orthogonal one to each other, and the norm of each vector is 1. And then, any vector in X have this representation, but this is a series. And we call this number from here the Fourier coefficient of X with respect to the orthonormal vector. Why we call this that? We have to go back to Fourier. Classical Fourier series, so what actually Joseph Fourier did, he wanted to solve the diffusion or the heat equation by searching functions of this type. Again, we have a series here, but we have here the cosinus of kt and the sinus of kt. Yeah? So these are actually, they are actually making the orthogonal system. So for n equals 0, we have 1 divided by 2 pi, just a constant function. And for k, 1, 2, and so on, we have the functions 1 divided by pi cosinus of kt and 1 divided by pi sinus of kt. So they make an orthonormal system with a little bit of imagination, but we have to push it. Rather, imagine this three-dimensional orthogonal system in R3, but imagine it in infinite dimensions, if you can. So this is what is done here. And for audience that like music, music is already here. So actually what you hear is exactly such a thing. It's not a series because our ear cannot hear frequencies higher of 20,000 hertz. So it's just a truncation of this. So what actually you are hearing, you are using exactly, you are hearing some of this cos kt and sin kt, and you are hearing exactly this a, k, k, which are called the harmonics. So every sound, if you know what the timbre is or the color of the sound, has some higher harmonics. And this is how music is coming. So if you want to understand music, go into Fourier series and you will understand a lot of it. Yep. Yeah, like that. Students in electrical engineering, this is what they are doing most of the time. This is how the computer-generated music is obtained nowadays. They know the spectrum of a sound. So to know that there are these devices, electronic devices for playing. It looks like a piano, but you can imitate practically any instrument by choosing the correct harmonics and the correct coefficients A, K, and K. You can generate any sound you want. Okay, now just to give you an idea how difficult this problem is finding orthonormal basis, I'm giving 3 classical examples: Legendre polynomials, Hermite polynomials, and Laguerre polynomials. Please.
Shouldn't you also need to specify the weighted unit product as well?
No, here we are always using the Laguerre measure. On -1, 1, on the real line, and on the semi-axis, we always have the Laguerre measure.
Are those in domain?
Yes. So -1, 1 is in the case of Legendre polynomials. Here we are working with functions defined on the whole real line. And here we are working with functions on the positive semi-axis.
So the subinverse, see.
We are always taking complex values. All our Hilbert spaces are complex values because, you know, there is a problem with the real field is not algebraically complete.
The eigenvalues can be complex.
Yes, yes. Many times eigenvalues can be complex. Okay, this is just an idea. Now, the Dirac model versus von Neumann model for quantum mechanics. It was a really big trouble for a very long time how to reconcile the Dirac model with Bra and Katz with the von Neumann model. And it was a French mathematician, Laurent, who solved this by his theory of distribution. I think that Schwarz was one of the first recipients of the Fields Medal in 1950, if my memory is correct. The first recipient of the Fields Medal in 1950 was Laurent Schwarz.
No, not the first one.
Okay, one of the first, I said. Yeah, but it is given every fourth year, so it was just at the beginning. Okay, anyhow, he did this by his theory of distributions. And so he defined this space D of omega functions which are infinitely many times differentiable, but they have compact support and with a special topology. And then the dual space, which is a vector space of continuous linear functions, forms.
Before doing that, for example, product polynomials are not automatically with respect to the net measure, but
No.
The measure is minus x per root.
It is a scalar. It is just a scalar. It's not a weight function. It's a scalar. It's only normality which might be a problem. Okay, and this is actually reconciliating the von Neumann model with the Dirac model, because here is what von Neumann is doing. He's working in vector spaces, but here is what Dirac is doing. His bra and his cats. No. Schwarz actually showed the following, that Dirac and von Neumann model are pretty much the same, but you have to look it in a different way. So in the different differential equation forms, here you have the weak solutions, here you have the strong solutions. Okay, it's a long story about this. Yep. This one, it's a continuous embedding. So all these spaces have topologies, and the inclusion is continuous. The inclusion operator is continuous, which means that this topology is stronger than this one, and this topology is stronger than this one. Please. Yes, D prime is a dual of, it is a space of continuous linear functionals, and this is what we call generalized functions of distributions. Now, just briefly, what is this mathematical model of quantum physics? Any isolated physical system is associated to a Hilbert space, which we call the state space. The state of the system at the fixed time is a vector, it's a unit vector, usually in H. Physical observables are represented by the initial operators. And this is the thing that I want to emphasize. So if you want to talk about quantum physics, you need to have states. States are vectors in a given Hilbert space. But you need observables. What does it mean, observable? Some quantities that you can measure. And these are linear operators. And there is a quantization of this. So the spectrum of the observable is actually what usually physicists can measure in doing experiments in their laboratories. And if you have eigenvalues, they are exactly what they are measuring. So eigenvalues, again, it's prevalent into quantum physics. Please.
Talked about permission operators. Are we using permission the same way as Spectral physicists or
no, we are using in the weaker sense. Self-adjoint is a stronger assumption. But anyhow, here it's the difficult part. We have to use spectral theory in order to do physical interpretation of the physical quantities that we are doing. So observables of if you have the observable given by the linear operator A, then the state must belong to the spectrum if you are doing that measurement. And then you have some probabilities. I don't enter into this. Right here, I'm using the Dirac notation of this. And if we represent the state in the basis formed by the eigenvectors of 3, then the square of the modulus of the component attached to a given eigenvector is a probability of observing. No? Because in experiments, nothing is for certain. You always have probabilities. And this is actually making one of the main reasons why we are so interested in these spectral theorems. Because we have to find the spectrum, and if possible, we have to diagonalize it. But they are infinite dimensional objects. So what does it mean, diagonalization? This is a big problem. Do I have some more minutes? Okay. Now I'm going to skip this part, apologies of your age. But now I want to tell you the stories of spectrum. Because spectrum as a concept existed in physics before Hilbert introduced it in mathematics. And what actually is something which is very strange, eventually it turned out that what physicists were calling spectrum is actually the same with what Hilbert was calling spectrum. So Hilbert used the name of spectrum independently of the physicist, but eventually it turned out that he was right. Actually, it is producing exactly this. Why? Because traditionally in physics, spectrum is associated with waves. And even more with signals nowadays. So this is a picture. It's a reformulation of a NASA picture for waves and at which level they are. Unfortunately, the audible waves are not here, they are here, because they are from 10 hertz to 20,000 hertz. So from here we have the radio waves, the microwave, the infrared, the visible spectrum, ultraviolet, X-ray, and gamma ray. So higher and higher frequencies. And now we have to give the definition, the mathematical definition of what a spectrum is. So we take a linear transformation and we call a point lambda is a complex number. Lambda is called a regular value if lambda I minus t is injective, the inverse is continuous, and the range of this is dense in the space. And we call the collection of regular values the resolvent set, and the spectrum is a complement. So if lambda is a complex number for which at least one of these conditions is not fulfilled, then it is called the spectral value. And the point spectrum is exactly the collection of eigenvalues. But unfortunately, there are two other parts of the spectrum: compression spectrum and residual spectrum. Fortunately, normal operators and self-adjoint operators don't have residual spectrum, but they may have a lot of compression spectrum. So now I'm just defining what a spectral measure is. So for students that know what a measure is, a spectral measure, it's a map associating to subsets in the complex field. So omega is a sigma algebra, operators with which property? They are non-negative. At 0 is 0, and for the whole space is identity. This is a multiplicativity property. The spectral measure for intersection is exactly the product, and this is the countable additivity property. So this is what we call a spectral measure, and then we can associate a scalar measure by taking vectors. And the first spectral theorem it's having this statement. Assume that n is a normal operator. Normal means the adjoint commutes with the operator n. In particular, if the operator is self-adjoint means A star equals A, like we have, for instance, in the principal axis theorem, then it is a normal operator on a hyperspace H. Then there exists a unique spectral measure where it is defined exactly on the spectrum. Spectrum of n is what? Is a subset of the complex plane. Yeah? Such that we have this very important part. N is the integral with respect to this measure of the identical function x. What is this? This is exactly in the principal axis theorem, the diagonalization operator, the diagonalized operator. You see, multiplication with an independent variable is exactly the diagonal operator. Okay, in addition, it can be extended to functional calculus ways. Okay, so this is the first form of the spectral theorem. I don't want to abuse my audience. I want to know if I can continue or we'll stop here and you can ask questions. It's a conflict.
We just talked about that.
Organizers?
Maybe we can continue until 7:30 and we stop there.
Okay, let me add 5 more minutes and then I will stop. I think it's probably too much. Now, this spectral theorem formulation is in terms of spectral measure. But there's another which is stated in terms of multiplication operators. What is the price we have to pay? The price we have to pay is that we are not going to work with measures in the complex field. We are going to work with measures, with abstract measures. So now, if you know what the sigma finite measure space is, this is x omega mu, if not forget it, but we have capital L to mu, the Hilbert space of square integral functions of x. Now, L infinity is a space of essentially bounded functions. Essentially means what? That we forget about small sets that have measure 0. For instance, if we have a countable set in the plane, it doesn't matter because for the Lebesgue measure, they have measure 0. Yeah? And then we can define such a function. You can imagine it as a bounded function, yeah? A function which is bounded. We can have this multiplication operator from L to L. What does it mean? Is it the m phi of the function f? It's just a multiplication of this phi. And then I'm jumping to the spectral theorem multiplication operators. For any normal operator of a stage, there exists a measure space and the function phi in infinity, and the unitary operator from H into L2, such that n phi conjugated with u and its inverse. Do you remember now the principal axis theorem for n equals 2, how we got it? Yes. It was exactly in that way. Yeah. So u is analog of the orthogonal transformation, and the multiplication operator is analog of the diagonal matrix with the eigenvalues on the diagonal. But you know, at this level, it's very difficult to recognize it. There's another one, the third form, which is actually a spatial case of a von Neumann theorem for commutative von Neumann algebras in terms of spectral multiplicity. Okay, students that are still interested to know it, I have to a recommendation that can be found on the internet. The master thesis of my student said that is called the spectral multiplicity theorem. It can be found on internet. And if you want to understand it, please go and download it. You're going to need at least 1 year to understand it. And a lot of mathematics. Okay, I think I will stop. Thank you. Questions now? No. Please.
It's always possible to expand the vector space in terms of eigenvectors of when permission operator. I mean, shouldn't it be at least bounded?
You mean the vector or
The operator.
no, it's not necessary to be. If it's self-adjoint in the strong case, you are getting a complete orthonormal system, which means it's a basis, and you can always find it. Actually, thank you for the question, because we can go back now with these ugly formulas. Each of these system of orthogonal functions in the corresponding L2 space for the segment, for the real line, and for the half line, they are eigenvectors of a differential operator which is unbounded. But with certain boundary condition in such a way that you make it self-adjoint. So it's not necessary the operator to be continuously bounded. Most of the differential operators are unbounded.
What kind of boundary conditions problems?
Well, it depends on the problem. It depends very much on the problem. Finding the correct boundary condition which gives you the self-adjoint is not an easy job. My former student who took a course on me on that, on unbounded self-adjoint operator, on this, he can tell you a lot of things, how difficult it is. So somehow my goal was, I don't know how much I succeeded, showing you that the origin of these spectral theorems is actually conic sections. 2000 years ago.
Is there a connection between the big L2 and the small L2?
Yep. The Fourier transform gives exactly the isomorphism between these two. Yeah. Thank you. Please.
Can you comment on the operators? Do they consider the same set of eigenvectors?
You mean N and star or what?
Any
Okay. If you have two operators, normal, and they commute, what can you say about their spectra? And yeah, they have very close spectral picture. They have very close spectral picture, but not in the sense of the eigenvalues, but in the sense of the eigenvectors. The spectral spaces should be somehow similar, or at least orthogonal. Either coincide or they are orthogonal.
and you find the operators
Yeah. Okay, there are basically only two things, two ways. One is with series, and the other is with integrals. But in a more general picture, any integral is actually a series. So the answer is no. This is the only picture of the inner product. If you take a discrete measure, if you know what it is, you are getting exactly, you are transforming an integral into a series. Yeah, okay.
Doesn't mean it's showing structure.
Sorry?
should be right for that it's series are actually integral fluids.
Yeah, because that's what I say, any series is an integral. You can talk about well, even integrals are series, you have a little bit broader understanding of it. So this is actually the nice part. This is actually coming from here by this.
Yes.
So sigma migrated into S and then elongated, you got the integral sign. This is the origin of the integral sign. Please.
So if you want to make the historical, right, you think you have lots of names in there.
Yeah.
Basically, maybe all of you and it's not regulation. But I want to ask you if you think that, like, what was the motivation for introducing more and more abstract theorems or more and more abstract results? Like, if they just ask, oh, with this something that only works here, can you take there something more than abstract? What was the motivation behind it? Especially I'm interested in the part where it's because it's not clear to me whether they developed the math in order to figure something out that they were obtaining in the physical sense or experimental world, or whether it went the other way around, that math went independently, and then physicists look and say, oh, I know some math.
Thank you for the question. Actually, no, because I got this question many times. If I am in a society and eventually I have to confess that I'm a mathematician, there are two kinds of reactions. One is horrible. I remember my childhood. That was, come on, what happened to me because of mathematics? It's horrible. But then there are other people. They are saying, what actually do you do? Well, okay, I do mathematics research, but what kind of problems are that you are solving? Okay, and the answer here is twofold. Most of the time, we do mathematics from scientific curiosity. What is happening if I have a different framework? But we also do mathematics which come from problems from natural sciences. In the case of quantum mechanics, the situation is mixed. So a lot of mathematics already existed before, and this physicist realized that mathematics is good for modeling this, but many times the mathematics does not exist. And physicists are challenging us with this question. Come on, in order to play with your toys, abstract toys, try to solve this question, which I need desperately, I need it for the problems I have. So somehow the job of mathematics is controlled in this way. We have the freedom of mathematics done by curiosity, but we also have problems coming from mathematical models that we want to.
So you think that even like, I mean, I can't think of an example, but even like in physical models, you think, oh, I need to go to more abstract mathematics in order to solve that physical problem.
Yeah, sometimes.
One common view for people who are neither mathematicians or physicists, they think, oh, we do that computation, so you just need to find something computational and practical. You don't need to go to these very high. So that's something that I'm interested in.
And unfortunately,
Because if you feel something,
unfortunately, the situation is bad in the sense that we really, most of the times, we need that level of abstractness. I mean, think about the Neumann model of quantum mechanics. You need a Hilbert space, which most of the time is infinite dimensional. Now, everything that physicists are doing, and in quantum physics, they cannot actually look at the objects like you are looking in classical mechanics. You see, there is no way to see. So the only tool they have in order to understand quantum physics is through mathematics. There is no other tool. That's why I call mathematics the sixth sense. Yeah? We have our five senses on exploring this universe, but if we want to explore the universe at the quantum level, we need mathematics. There is no other tool out of mathematics, unfortunately. Please. Well, they're not quite similar. The trouble is the following. First of all, they are not quite polynomials because they have these exponentials. Yeah? But the trouble is that here you are working with functions on the whole real line. You want somehow that at infinity, they should get zero, close to zero. That's why we are using this weight function. In this case, we are using a milder function, e to the power minus. But both this function is vanishing at plus and minus infinity. This function is vanishing at plus infinity. So they're not quite similar. Yeah.
What do we different forms? Are they probabilists or different forms?
No, it's physics.
Oh,
They are exactly the eigenvectors of a certain differential equation. Yeah.
So, we thank you for your talk.
Thank you.